Hello everybody and thank you for joining my presentation. I'm Álvaro Mateos González from New York University, Shanghai, and this is work in collaboration with Laurent Mertz, Minh Tang and Yingyi Fu. So I've also added the logo of the University of Montpellier where I was when I started this work. I'm going to talk to you about the stochastic dynamics of some confined biological microswimmers. So what are these? These are cells with a motile flagella that that experimentalists put into a solution confined between two glass plates, and they observe the motion of these microswimmers in the solution. So the red dots in graphs B and C represent successive positions of an observed microswimmer, which allow us to recover, allows experimentalists to recover a trajectory of the microswimmers. You can see that at some points the trajectory is detached from the boundary, at some points it becomes attached to the boundary and can detach again. So important data that can be recovered are the distance between the microswimmer and the cover glass, Z here, and also the angle theta that the swim direction forms with the horizontal plane of the cover glass. So Z and theta are the important variables in this problem. Now, if you let the microswimmers swim in that solution for a very long time, you actually observe that they tend to concentrate in the vicinity of the boundaries. 0 and 200 correspond to the positions of the two cover glasses. And this is consistent across different types of microswimmers. So we've got spermatozoa, E. coli, and so on. Okay, how to this? You also have some other types of data that you can recover from these experiments. Specifically, this is the collision angle at first collision with the boundary as a function of the start angle for a microswimmer that's launched in the middle of the solution. You have all the types of data that you can recover from these kind of experiments. So, how do you describe these experiments? Basically, in the literature, there's two families of models. One of them deals with the velocity fields that are generated by the motion of the flagella of these cells, as well as the whole cell, of course, and how this motion generates a velocity field in the fluid, which in turn affects the velocity position of the microswimmer. So these are hydrodynamic models, and there are also some models which abstract the hydrodynamic aspects and into just saying that the microswimmer moves in a certain way. So you've got a free swim with some white noise in position and direction, and you also have some reorientation at contact with the boundary. Well, of course, there's also models in which you have a round tumble, but for the purposes of this presentation, let's start by these white noise models. How does this work specifically? So, for the hydrodynamic models, what you have is a velocity field in the fluid. The velocity fields here are represented by colors between blue and red for lower and higher velocities, respectively. You have field lines represented in figures A, B, E, and F. Okay, figures ABC corresponds to what happens close to far from a wall, so far from the boundaries of the domain. And the bottom graphs correspond to what happens close to the boundary of the domain. So, left column, A and E correspond to observations. That's why the lines are a bit wiggly and not perfectly straight. Right-hand columns correspond to an idealization of the microswimmer as a force dipole. So, B here, what you have is the velocity field generated in the fluid by a force dipole. If you consider that the microswimmer is a force dipole, you get this solution of the Stokes equation, and that corresponds quite closely to A, as you can see from graph C, which is a subtraction of B from A, except that close to the microswimmer, you've got some differences. You have some red close to the microswimmer, and far away from the microswimmer you've got only some blue and green. So actually the force dipole approximation is quite good far from the microswimmer, but really close to the microswimmer you've got some problems. Same thing happens close to a wall. So near a wall, the thing is that the fluid the fluid velocity field is different than far from a wall, of course, but you also have these kind of good approximation a bit further away and not that good very close to the microswimmer. So these hydrodynamic models can predict the terminal distributions of the microswimmers, but they overpredict what happens close to the boundaries. So they overpredict the accumulation close to boundaries. Now, For the rotational diffusion and reorientation at contact models, we're going to follow the literature by Lee, Tang, and co-authors. So they consider the microswimmer as some kind of rod, which well, is defined by distance from the cover slip y, and an angle of a swimming angle theta, as we've said previously. These equations, delta y and so on, are used for numerical simulations. That's why they're written in terms of increments. So these correspond to stochastic differential equations, of course, if you rewrite them. Psi and sigma are normally distributed random variables. So what you get here is that the microswimmer is going to advance in its direction, but with white noise in space and white noise in angle. Of course, this happens when there's no contact to the boundary, and when there's a contact to the boundary is going to exert a force on the microswimmer at the point of contact, which is not the center of mass here. So this leads to a torque, which in turn makes it so that the microswimmer is going to align with the boundary. So there's a given rotation rate, which is the dotted line here, depending on the angle that the microswimmer forms with the boundary, and the full line represents the time that it's going to take the microswimmer to align with the boundary. Okay, so that's the type of model. It also predicts the distribution of terminal density quite accurately, except, well, these positions. There's a sharp turn in the model, which is a bit weird, and there's an under-prediction of the density. If you look at the overlay here, this corresponds to different terminal density profiles depending on the angular diffusion coefficient. Okay, what happens if you follow Bianchi and co-authors is that these models correspond to two different types of phenomena that have different relative importances at different distances from the boundary. So at boundary contact interaction, of course, is predominant, but from 1 to 3 microswimmer lengths from the boundary, hydrodynamic forces play an important role that's not really taken into account in the Lee and Tang literature. So these hydrodynamic forces hold back the microswimmer close to the boundary, especially if the microswimmer is parallel to the boundary already. And they also tend to make it so that the microswimmer will align with the boundary. Further from the boundary, both types of models do a good job, actually. So what we want to achieve is that we want to provide a framework in which we may include both types of interactions, so hydrodynamic interactions and contact interactions, without giving any a priori, without giving any a priori discrimination between both types of interactions. So we want to solve some kind of inverse problem in which the reorientation torques will be deduced from the experimental data. How do we do this? We start with providing a 3D model of the microswimmer. So this is minus L, that's the position of the horizontal cover slip that's at the bottom. L, that's the vertical position of the horizontal cover plate that's at the top. Z is going to represent the position of the microswimmer, the vertical position. Theta is the same angle that we introduced previously. V here, which we introduced, equals sine theta. This is going to be a type of normalized vertical speed. So, just going to skip quickly across this. We follow Lee and Tang in the fact that we have free motion phases and boundary contact phases. And in both of these phases, we consider that there's a reorientation torque, which we are not going to express in any specific way. We just say that there is a reorientation torque, which we will later define. Okay. At boundary contact, the variation in position is 0 until the velocity orients away from the boundary, of course. Okay. And by means of Ito's lemma, we can deduce the equation that governs the evolution of V, the normalized vertical speed. Here we have a torque term, F. Okay. Now, this gives us a stochastic differential equation for the full motion, in which you can see that in the interior of the domain, in the space, we have a certain expression, and on the boundaries we have a different expression for Z. These two expressions can be combined into one, by means of stochastic variational inequalities, which we will show you a bit later. Okay, so for now, this is an agent-based simulation of the position and angle of a microswimmer with no reorientation torque term. And this is what happens if you launch that microswimmer vertically in the middle of the domain and at initial time, and you measure the first impact angle. So these are impact angle distributions depending on the angular diffusion coefficient. Larger angular diffusion means that the sign of the angle of impact is going to be closer to -1 or 1, so it's going to be more perpendicular to the boundary. Okay, so by means of stochastic variational inequalities, we may absorb the excess displacement by the boundary into this scalar product, and we may conserve the reorientation torque term. Okay, we are going to do some relatively standard procedures in order to achieve the Kondo-Graph backward equation, and once we have that, we are going to use some stochastic control tools to target terminal distributions by choosing the reorientation torque in an appropriate way. What do I mean by that? We begin in a given probability space, omega fp, which we're going to condition for a terminal impact angle, v star, at first boundary hit time. Okay, I'm going to skip quickly. The idea is that we're going to change probability space in order to have this term appear, and here what we recognize is the reorientation torque about which I talked previously. So in the condition space, recall that this is what happens if f equals 0. In the condition space, we're able to target a terminal first hit angle, and we can recover the kind of optimal, let's say optimal between the optimal reorientation torque term, and we can recover as well the impact angle distribution which we were seeking. So just to sum it all up, we've provided a 3D model of a confined microswimmer with a torque term which is a priori undefined. We have used stochastic variational inequalities in order to provide a unified description of these two phases, contact and free swim. And this is the unified framework. We've included the reorientation torque with few a priori modeling restrictions. We have shown that it's possible to numerically recover an optimal reorientation torque and a target first impact angle. Now, what we've started to do is defining some short cycle, long cycle patterns in order to be able to use the full trajectory data to exploit all of that with stochastic control tools in order to use the optimal torque. So thank you very much. I'm sorry for the excess time. And if you have any questions, please, I'll be glad to answer.